Today we're going to talk about warp space-time. My name is Jackie and I'm with the ARC Center of Excellence for Gravitational Wave Discovery, or OzGrav. So when we think about space, we think about things that can be found in space, such as stars and galaxies and planets, and we know these things are in space because either we can see them with our eyes, or if they're small or far away, we can use telescopes. But we do run into a problem if objects don't emit light. How do we see them? Well, one of the objects that does not emit light in the universe is something called a black hole. Now, a black hole is a stellar remnant from a very large star that has reached the end of its stellar lifetime. And black holes are very small, and you have many times the mass of our sun squeezed into a fairly small space. For example, if our Earth were squished into the size of a marble, that would be about a black hole. So black holes are so dense that not even light can escape. So how can we detect them? Well, we look at how they interact with other objects. And we do this by understanding principles of gravity. Many scientists worked over many years to develop rules related to gravity and gravitational interactions. Galileo studied falling objects on Earth, and Kepler studied orbits of objects in space. Isaac Newton is the one who put these two observations together into one law of universal gravitation, saying that two objects that have mass will interact, they will attract, and that interaction, that force of gravity, will depend on how massive the objects are and how close they are. However, his theory of universal gravitation didn't quite match all of the observations that were made for objects in space. So it was a very good approximation, but wasn't the best model for understanding how objects with mass interact. That's where Albert Einstein came in, and with his theories of general relativity, he actually looked at gravity not as a force, but as the distortion of the fabric of space. And what we're going to do is we're going to explore a gravity well. So we're going to watch a little video made here in Melbourne during social distancing, in which we will stretch out a sheet and to represent the fabric of space and use various size balls to represent stars and other things that may move through space. So let's go ahead and check that out. There'll be some times when you can pause and think about your answers and make predictions, and we'll come back together once that video is done. Welcome to the gravity well demo. I've got 4 helpers that are going to stretch this black sheet as much as they can. When it is flat, that is going to be a model of empty space. In empty space, there is nothing else nearby that will affect the object moving through that space. If we put an object into motion on our flat fabric of space-time, what type of path will it travel? Let's pull our fabric of space-time nice and taut so that it acts like empty space. Here is our light mass that we will roll through our space. Let's test your prediction. We're going to roll the ball, and we are going to see that it is going to go straightish. So objects moving through empty space will follow a straight path unaffected by outside influences. But now we're going to put a large mass into our fabric of space. This is going to represent a star or a black hole. It's going to cause our space to curve, and notice that the fabric bends. Now we have a really heavy object bending our fabric of space, and notice how the fabric distorts. This is what happens in real space. Massive objects distort the fabric of space-time. Now we're going to put a small object in our fabric of space. What type of path will it travel? Pause to make your prediction. And now we're going to test it. Before we do that, let's just take a good look at this curved space. Ours is only 2D. The actual fabric of space-time is 4D. 3 dimensions of space and 1 of time. We're going to predict the motion. And now we're going to test. We will see what a small object does when passing through the curved fabric of space. Did you see that? It followed a curve. So the fabric of space is curved, therefore the object moving through the fabric of space follows a curved path. This is Einstein's theory for gravity. Einstein's theory of relativity also takes into account that light will follow the curved fabric of space. Light will follow the curved fabric of space, which means that objects that are emitting light and near a black hole, their light that we see will be distorted. Here you can see the light around the black hole being distorted. We're going to look at this using an app called Pocket Black Hole. Pocket Black Hole is an app developed by the University of Birmingham, which allows you to use your phone to create black holes and see how the image in front of you would be distorted from that black hole. You can use it in selfie mode, you can use it in rear facing mode, and then you can also use it in looking at a grid of space. It is available free on the various app stores for you to download and use to investigate. So hopefully by now you've seen that we have some black hole basics that we've covered. They are so dense that not even light can be emitted from them. However, we have developed other ways to observe them, mainly by looking at how they interact gravitationally with other things in the universe. We've seen that they can warp the fabric of space, and other objects will follow that curvature in the fabric of space. And even though we didn't cover it here, we can also detect them when they collide by looking at the waves in space that they emit. Those are called gravitational waves, and that'll be another lesson.